In this video, we'll see how we can control some addressable RGB LEDs, for example, NeoPixels, WS2812s, and in this case, we'll control some SK6805 RGB LEDs. We'll do this using an STM32 U5 microcontroller on the PCB you're seeing here, hooking up a timer channel, which is generating PWM with DMA to offload the CPU. We'll go through all the steps, looking at both the hardware, the datasheet, and then implementing that in firmware with a very small driver. And you can see this is actually quite a straightforward implementation, where we're starting all the way from the basics of the datasheet and then implementing everything ourselves. The PCB you're seeing here will be used in many future videos. This is actually a micro quadcopter controller PCB, and I'm currently in the bring up process, so testing out all the peripherals, writing all the drivers. I'd like to show you how I went about this in a series of videos. The board is either battery or USB powered, features USB battery charger, 4 micro DC motor drivers, various sensors such as inertial measurement units, magnetometers, barometers, and so on, as well as an RF CC2500 2.5 GHz transceiver. But more on that in future videos. In this one, we'll focus on writing a driver for some RGB addressable LEDs. A huge thank you to PCBWay for sponsoring this video. I had these Bumblebee quadcopter PCBs manufactured and assembled by them in China, and they did a fantastic job. For this, I used their PCB prototype service, which is very customizable. I went with a matte black solder mask and yellow silkscreen, which I think looks particularly cool. And also, I went with their turnkey assembly service. I'll leave a link to them in the description box below if you'd like to check them out. Make sure to follow PCBWay on Instagram, where you can check out all the cool designs they are producing. And occasionally you'll see some of my designs pop up on that Instagram account as well. What we'll be focusing on today in this video is using the centerpiece, this STM32 U585 microcontroller, which is, so to speak, the brain of this PCB, which interfaces with all these peripherals and sensors. But also on the left-hand side, you can see at the top and at the bottom, above and below the USB-C connector, are these very small RGB LEDs. And rather than having 3 separate channels for the colors, so for red, green, and blue, these RGB LEDs have actually a tiny controller inside, which takes in some amount of data per LED and can also feed data onto a series or a chain of LEDs. So you can actually cascade them very easily with a single channel of data. To control these RGB LEDs, we'll go through the datasheet. We'll write our own firmware for this STM32 U5 microcontroller. You'll see this is actually fairly straightforward once you've understood the datasheet. For this, again, we'll be using a timer channel along with DMA, and I'll show you the whole setup. Let's briefly get familiar with the hardware and the connections of this Bumblebee PCB so we can understand what we're implementing later on with the firmware and what connections we need to make. For power, we can either provide power via USB connector or attach a battery to the top 2 terminals. For this video, I'm just going to use the USB Type-C connector, which powers this board through various regulators. Then we'll use the STM32 U5 microcontroller in the center and address the top and bottom RGB LED. Briefly jumping over to the schematic, in terms of power, we have the USB Type-C connector, which actually goes through a battery charger and boost converter, which handles all of the charging and configuration for the battery, which is also hooked up to this device. The output voltage is then this VSys voltage at the top, which ranges anywhere between 3.7 and 4.2 volts, regardless of the discharge level of the battery, of course within safe limits. So VSys is between 3.7 and 4.2 volts, and that I feed into a 3.3 volt regulator, which gives our main 3.3 volt rail, for example, for the microcontrollers and sensors. The VSys connection, however, again 3.7 to 4.2 volts, is used for the RGB LEDs because they have a minimum voltage of 3.7 volts, which I took from the datasheet, and we'll see that in just a second as well. So that's why we can't, or we shouldn't rather, drive this RGB LED from less than 3.7 volts. That's why this is connected up to VSys. Per RGB LED, we have 4 pins. We have power and ground. At the top and bottom, we have a data input pin on the left and a data output pin on the right. The great thing is about these RGB LEDs that we can cascade them, and we can cascade quite a number of them. What happens is that each of these RGB LEDs has a certain requirement of bits of data. This happens to be 24 bits for this type of RGB LED. And if we send in more than 24 bits of data, assuming correct frame formats and so on, the RGB LED in series will take its first 24 bits of data, use it, discard it, and then pass the rest on from its data output pin to whatever follows. In this way, we just need one signal line, which is this RGB LED line, which can drive a whole string or series of these RGB LEDs rather than requiring many different channels driven by PWM and so on. In this way, these are very nice, and this is why they're called addressable RGB LEDs. It's a single serial data link from a processor or some controller into an RGB LED, and that can then be cascaded with a number of these. The actual RGB LED connection, if we go to the top right of the schematic, goes to this STM32 U585 microcontroller, and we can see that's hooked up to pin PB1 or pad 19. and this happens to be a timer channel, as we'll see later in the firmware setup. What we also have to see is that this microcontroller actually runs off 3.3 volts, and we have to keep in mind the logic levels of the RGB LED. With the microcontroller being at 3.3 volts, we have to be aware of any logic levels and I/O logic levels, given that the RGB LEDs have a minimum system voltage of 3.7 volts, and I believe they can go up to about 5 volts. So with VSys between 3.7 and 4.2 volts, depending on battery charge level, are the logic interfaces for the data in pin coming from the microcontroller, are they going to be okay? And from the datasheet, we can extract a table that the high logic and low logic levels are 0.7 VDD and 0.3 VDD respectively. So therefore, for a VDD level of 3.7 to 4.2 volts, which is our VSys, we have a logic low level of 1.1 to 1.3 and a logic high level of 2.6 to 2.9 volts, which is perfectly fine for our 3.3 volt logic sent from the microcontroller coming to the first data in pin of the RGB LED. But keep in mind to check your logic levels for these RGB addressable LEDs. With that being said, let's move over to the datasheet to look through this in more detail before we write the firmware. If you have a different type of RGB LED, so these could be these WS2812s or any other variant, they are usually very similar with the control and also with the pinning of these interfaces. So hopefully the content in this video will be useful regardless of what addressable RGB LED you use. In any case, in this video, we'll be using the SK6805-EC15. I chose it because it's very, very small. It's 1.5 by 1.5 millimeters and does everything those other addressable RGB LEDs does as well. And it's plenty bright for this application. There are many different datasheets floating around. I believe this is originally a Chinese part, so the original datasheet is actually in Chinese. So we'll be using this translated datasheet, but there might be some maybe spelling errors or translation errors in there. But for the most part, this seems to be right, and I've got it working on my end. Looking through the datasheet, again, we have our various pin connections. Again, the nice thing is we can cascade these LEDs. We don't need any special LED drivers other than that serial controlling from a host controller, for example. We can see here are the recommended operating ranges. Again, VDD is from at least 3.7 volts to about 5.5 volts. Now, I have heard people driving these LEDs at 3.3 volt VDD, but I'd suggest staying within the recommended operating parameters. This is the table 10, where I got the logic high and low levels from, and keep in mind this is for a test condition of VDD 5 volts, but I've got it working on my end. Now let's actually start thinking about how we can control and address these RGB LEDs. Again, we send a control data signal, various bits coming from a host controller to the first RGB LED. That does something with that data, passes it on to the next LED, and so on, and you can build a chain of these RGB LEDs. The data itself you're passing in is coded. So we have a certain code frequency or symbol frequency, which translate to symbol period. So at every symbol period, after, if we look at these timing waveforms here, so after t seconds have elapsed, that is one symbol. One symbol can either be a 0 or low code, or it can be a 1 code, a high code. And for example, for the low code, we have to have the signal high for a certain amount, which is given by TOH, and we have to have the signal low for a certain time period, which is given by TOL. If you want to send a 1 code, instead we have to have the signal line high for a different amount of time, this is for T1H, and the signal line low for a different amount of time again, which is T1L. So we can send either 0 code or high code by changing how long for a certain symbol period our data line is high and how long it is low for. Lastly, we do also have a reset code, which will become important later on, where we simply keep the data line low for a given amount of time given by TRST or T reset. So again, we have a symbol period, which is fixed, which is T, and T is 1 divided by our signal frequency. Then we have the low code and the high code, and effectively all we're doing, the difference between the low code and the high code is we're varying the pulse width. So we have a fixed transmission rate, transmission frequency, but we are varying the duty cycle of our waveform. So as you can probably tell, this is simply PWM. For low code, we have a shorter on time, which is a lower duty cycle. For high code or 1 code, we have a longer duty cycle or longer on time. The question then is, how many of these bits do we have to transmit per RGB LED? And it turns out these are 24 bits. So it's a combination of these low and high codes, these varying duty cycles, and 24 times per RGB LED. The actual then full data structure per RGB LED is 8 bits of green, 8 bits of red, 8 bits of blue. So for example, if we have G7 to G0 all sending a high code, so high code 8 times, and then the rest we just send low codes 16 times, we will get the full brightness for the green LED. So this is how we can change, for example, the brightness of these various colors, mix these colors by simply sending low and high codes and 24 bits of them with this specific frame format. So again, we're sending 24 bits in this order, G7 to G0, so most significant bit first, then red, most significant bit first, R7 to R0, 8 bits, then blue, most significant bit first, B7 to B0, 8 bits of blue data. Green, red, blue data, 24 bits, using low and high codes, we're just varying the PWM duty cycle. This is all fine and good for one single RGB LED, but we of course have that cascade of RGB LEDs. So the question is, how do we do that? In my particular case, for this particular PCB, I simply have two RGB LEDs, RGB LED 1 and RGB LED 2. So what we then do for two RGB LEDs, we simply cascade the first 24 bits for the first LED, and then another 24 bits for the second LED, and then we send a reset code. So we send 24 bits for the first LED, 24 bits for the second LED, and then we send a reset code, which is simply keeping the line low for a certain amount of time. And we can already see here the reset code, the line needs to be low for at least 80 microseconds. So now we know the basics of what we need to do. We have to modulate the PWM per bit, and we need to send 24 bits per RGB LED, and at the end we have to send a reset code. So let's see how long these symbol periods and codes actually have to be. And for that, we just have to go a tiny bit up to the table number 12. And here we can see that the T reset code at the bottom, the low level has to be at least 80 microseconds. So we have to keep the line low for at least 80 microseconds. And that makes the RGB LEDs latch that data. For the symbol period, we see right at the top, T, we have a symbol period of 1.2 microseconds, is a maximum symbol frequency of 833 kilohertz. So we can run our PWM frequency at a maximum of 833 kilohertz, but ideally we should be at a lower frequency and therefore a longer symbol period. Then we can see, for example, the low code high time should be around 0.3 microseconds, and our one code high time should be around 0.6 microseconds, but we do have a range given this data table here. But we should stick around these standard values, but not exceed the minimums or maximums. So with all of this information in mind, let's move over to the firmware and see how we can actually implement this on the STM32 microcontroller. Please excuse this awful paint drawing, but what we want to do in firmware is use a timer at a fixed frequency, which has a symbol period T. So 1/T is our timer frequency that we set as fixed. And all we do is change a register in the timer that controls the duty cycle, or rather the pulse width, for how long per symbol period the data line is high or low. In this way, we can send these low or high codes for the different bits of the RGB LEDs. So for green, red, blue, 8 green, 8 red, 8 blue. We can do that for one LED and then for the second LED, and then we can send the latch reset signal, which is just keeping the line low, so it's 0 duty cycle for an amount of time. So this is drawn very crudely here for just one LED. Let's say we start our new sequence. So we start at bit green 7, which is the most significant bit of the green RGB LED, and this is an 8-bit value. So if we send a 0 code as our green 7, we would set our duty cycle to be given per the datasheet. Then after one symbol period is elapsed, we change our duty cycle to give a 1 code, for example. So we have a longer on time. And for green 5, we do another code, 1 or 0. We loop through all the greens, all the reds, and all the blues. And for a single LED, all we would do is then keep the line low for this T reset amount of time, and that would then latch and update the LED. For two LEDs, we simply have to loop these 24 bits twice, 24 bits for the first LED, 24 bits for the second LED, and then do our latch and reset. And for more LEDs than that, we just cascade these 24-bit values. But always at the end, we have to do this latch reset step where we simply keep the line low for a given amount of time from the datasheet. So now let's move over to CubeIDE to see how we can program this. In CubeIDE, which is the free development environment for ST microcontrollers, I've created a new project with the specific microcontroller part number I'm using, this STM32U585CIU6, and here we are in the pinout configuration window, this IOC window. Quickly jumping back to Altium Designer, again, the RGB LED pin is pin 19 PB1. I also don't have any external crystal oscillator connected up to this, and what we'll be using for programming is this serial wire debug connection via this tag connect debug header. So looking at PB1 on the microcontroller, this is the bottom pin in the center. If I click on this, we have various different options. What I chose, and this is what I pre-planned for this hardware, is that I want this timer 3 channel 4. So I'll click on timer 3 channel 4. What I also want to enable, if I go to the left-hand side, trace and debug, click on debug, expand this, I would like to enable serial wire debug just for our programming and debugging. And now we want to configure the timer channel. So now we have debug enabled, the timer pin is set up but not configured yet. But before we configure the timer channel, let's go over to the clock configuration. Again, I don't have an external crystal set up for this, so I'm using the high-speed internal crystal oscillator, which is typically 16 MHz for this part. If I type in 160 for my H clock, effectively my core clock frequency, and then press enter, CubeIDE, after pressing OK, will search for the PLL settings that give us 160 MHz core clock for 16 MHz HSI. There we go. And we can see also on the right-hand side, we have the various timer, peripheral, and other clocks here. So they're all now at 160 MHz. And this is important for us to know because our timer frequency is derived from one of these clocks. In our case, they're all at 160 MHz. So that's our base frequency. Now going back to the pinout configuration, going to timers on the left-hand side and selecting timer 3, let me select clock source as internal clock, which then enables these parameter settings at the bottom. And we want timer 3 channel 4 because timer 3 channel 4 is mapped to pin PB1. Go to channel 4 and we want to generate PWM on that timer channel. And that now makes this pin go green. So now we have our clock setup, our serial wire debug setup, and the very basics of our timer channel, timer 3 channel 4 set up. This timer channel, set up as PWM, will generate the required PWM duty cycles and at the right frequency so we can send out our data bits to our RGB LEDs. Remember from the datasheet, we want our symbol period to be fixed, which is capital T. This will be our core timer frequency. So timer 3 will run at a frequency of 1/T, which is F. Then we simply set the duty cycle to be either TOH or T1H, or rather the on time to be TOH or T1H to give us 0 codes or 1 codes. A reset code is simply an extended period of having a duty cycle of 0. So let's see what T needs to be. We saw that earlier. If we go up to the table, T is the code period, and that needs to be at least 1.2 microseconds. Again, to convert that to a frequency, it's 1 divided by 1.2 microseconds, which gives us a frequency maximum of 833 kilohertz. I would like to run my timer lower than this, at a lower frequency and something maybe a nicer number. So I will run it at a code period of 1.25 microseconds. So 1.25, and this gives me exactly 800 kilohertz. So our timer frequency, which is 1 over the code period time, is 800 kilohertz in our example. And that is okay because it's larger than 1.2 microseconds given here. A typical STM32 timer base frequency, or the PWM frequency, is given by the core frequency of the timer. And for us, this was this 160 MHz, which we saw in the clock configuration tree, divided by this auto reload register, +1, times the prescaler PSC register, +1. So we have to configure the ARR and PSC to give us a PWM frequency of 800 kilohertz. So there's of course many combinations we can do, but if we start at a core frequency of 160 megahertz and divide that by 2, we get a frequency of 800 megahertz, and if we divide that by 100, we get a frequency of 800 kilohertz. So it's 160 times 10 to the 6 divided by 2 and divided by 100 gives us 800,000 or 800 kilohertz. So therefore our prescaler is 2 and our counter period, which is our ARR register, auto reload register, is going to be 100. Keep in mind though, from ST's notes, the device itself will add 1 to both of those values, so we should subtract 1 from the prescaler to counteract that and from the ARR register. We could of course set the prescaler to be 100 and the counter period to be 2, but the counter period actually defines the minimum and maximum duty cycle. So our duty cycle can go, for a counter period of 100, can go from 0 to 100. So that's why I keep my prescaler at 2 and my counter period at 100, because that makes more sense to me, because then we can vary our duty cycle between 0% and 100% because our counter period goes from 0 to 100. The rest of these timer settings we can leave as default for now. However, we don't want to manually keep having to update the PWM values in software. We want to offload the CPU so we don't have to constantly send out these various PWM values. We want to do that differently, and what we'll be using is DMA, or direct memory access, so that'll be on the background. So very simply speaking, that'll be background transfers from memory to the peripheral, in this case the timer, sending out these bits of data to the RGB LEDs. To set that up, go to DMA settings. For this particular STM32U5 part, there's a different type of DMA, which is the GP DMA. So I'll click on Go to GP DMA, and we need to set that up. So I'll set up just the first channel, channel 0, to standard request mode. Click on channel 0, and the request is timer 3, channel 4. We will want normal mode. We don't have to keep sending data over and over again. We want to send it once, send the reset command, and that'll latch the data to the RGB LEDs. The direction for the DMA is from memory, so from our PWM values in memory to the peripheral, which is to our RGB LEDs from our timer. So it's memory to peripheral. Our source is the memory, and the source data width is going to be bytes, and we want the DMA to increment the source address automatically, but data width is bytes because we're sending values between 0 and 100, which fits in a byte. The destination is our timer, which is the duty cycle or the capture compare register. The The capture compare register actually has a data width of a word, which is 32 bits. So I'll set the data width of the destination to word. Let's just verify that again. Go to timer 3, parameter settings, and we can actually see the counter period or the pulse is actually a 32-bit value, which is a word. So that's why our destination for our DMA needs to be set at word. On the left-hand side, go to the NVIC and make sure that the interrupts for the timer as well as the DMA are enabled. And that's about all we need, so we can Control S to save and auto-generate code. For the sake of time, I've pre-written the driver header and source files, but I'd like to go through them in detail to see how they work. First of all, let's look at the SK605 RGB LED driver header. First of all, I need to include the specific hardware abstraction layer, if you are using one, of course, for the IC. So in this case, I'm using an STM32U5. I'm including the hardware abstraction layer because I want to use those functions such as the time and DMA and so on. And that's the way I get them into my header file, so to speak. Then I have a couple of defines. First of all, how many LEDs I'm using. On this particular board, I'm just using 2. Then what timer I'm using. And I'm using the handle HTIM3, which was our timer 3. And the timer channel is timer channel 4. Remember, this is just from the hardware, what we set up also in CubeIDE. So nothing particularly fancy here. The next bit is dependent on your timer frequency, and this is where we code in the high and low values or the 0 and 1 codes for the specific RGB LED we're using. Keep in mind, our duty cycle, we can set between 0 and 100, and we have a fixed frequency of the timer of 800 kilohertz. The question then is, how do we have to set our duty cycle between 0 and 100 to get these TOH and T1H values and the TOL and T1L values respectively to make sure we can transmit a 0 code or 1 code. So all we have to do is then set the relevant high and low values to be TOH or T1H, and because we have a nice duty cycle maximum or range between 0 and 100, all we have to do is a percentage. So for example, looking at the 1 code, we want our duty cycle to be T1H divided by T. So our 1 code has to have a minimum high time according to T1H of 0.58 microseconds and a maximum high time of 1 microsecond. So we need to convert that to our duty cycle since we're running off 800 kilohertz. And remember, 800 kilohertz gave us a code period of 1.25 microseconds. So if we have 1.25 microseconds, let's say we want to use the standard value for T1H, it's 0.6 divided by 1.25 times 100, and that is our duty cycle value we want, which is 48. And a duty cycle of 48 for our specific timer setup settings gives us a 1 code high time of 0.6 microseconds, which is within spec for T1L, which has to be at least 0.2 microseconds. So therefore, my define in the driver is that the high value is 48, which corresponds to 0.6 microseconds. Similarly, for the 0 code or the low code, our high time is given by TOH and our low time is given by TOL. So TOH, going up again, we want a minimum of 0.2, a maximum of 0.4, and a standard value of 0.3 microseconds. So again, we do 0.3 microseconds divided by our code period times 100, and that's our duty cycle. And we can see that's 24. Of course, it's just half of the TOH time. So that's why my low value or our 0 code high time is 24, which corresponds to 0.3 microseconds. So very easily, we've defined our 0 code PWM and our 1 code PWM, but also we want to define how many periods belong in a reset code. So how many times do we have to run the timer at 0 PWM duty cycle to give us the length of T reset? So T reset, again, needs to be at least 80 microseconds, and our code period from our timer frequency was 1.25 microseconds, and that means we need at least 65 low cycles. So for me, I've done 64 reset periods, which corresponds to 80 microseconds. So this is how you then can figure out the 0 and 1 code, as well as the reset code periods, duty cycles, and so on. Another define here is just how many bits per LED we have, and that's 24, and that bit order was green, most significant bit to least significant bit, red, most significant bit to least significant bit, blue, most significant bit to blue, least significant bit. Now with our defines ready for the 1 and 0 codes, or rather the high and low codes, as well as how many reset periods of duty cycle 0 we need, what we need to do is see how we then pass that data or store that data, then pass it to our DMA. We don't want to individually send or change the duty cycles of the timer one by one. So we send 1 bit, we change the timer, duty cycle, send another bit, and so on. We want to let the DMA stream do that. So therefore, we need a DMA buffer, which contains all of the duty cycles we want to send, and the DMA will then take care of that buffer, and periodically, every T seconds, every period, it will send out and set the next duty cycle for that timer, and in turn, that will then control the RGB LEDs. So therefore, actually the length of the DMA buffer we need, remember this is storing duty cycles, not bytes and not bits, it's storing duty cycles, is the number of LEDs times how many bits per LED we have. So every bit of an LED corresponds to one duty cycle. So we have 24 bits per LED, and we have 2 LEDs in this particular case. So therefore we have 48 data bits, so to speak, but those bits are actually duty cycles we are sending to the timer. That is not all we want to transmit to the timer, because again, to latch the data to the RGB LEDs, we need to send this reset code, which is simply keeping the line low for at least 80 microseconds. And that's why we add a length to the buffer. We computed that as how many reset periods where we have 0 duty cycle we need. This is how we compute the length of our DMA buffer. Now, how do we fill that buffer? How do we actually set the colors per these bits? There's many ways of doing that, but my preferred way is using a union. In this case, I have in this union one struct, which contains the RGB values, or rather, because of our bit order is green, red, and blue, and we have 8 bits of green, 8 bits of red, 8 bits of blue, so therefore we have 3 bytes. Green byte, red byte, and blue byte, and that is in a union with a UN32T, where actually we only need 24 bits of that data. So if we fill in G, R, and B, because of the union, the data value variable is also set immediately. So in this way, we just create per LED one of these unions. We set the G, R, B values of the struct, and that will automatically give us the data, which we can then use to set the duty cycles for our DMA buffer. Therefore, I create unions depending on how many LEDs I have. So I simply have an array of these unions, and that's where we'll be setting the color data. Then we have a DMA buffer, and the DMA buffer is using an uint8T data type. Again, this buffer is storing PWM duty cycles between 0 and 100. And then also I have a flag, which indicates once the DMA transfer has been complete, and then that lets us say we can send another stream of data if we're ready. Then I have 4 functions. One is to initialize, which is essentially to clear the DMA buffer. Then there's another function, set the color, which effectively just fills this union with RG and B values. We have one update function, which computes the DMA buffer and then starts the DMA transfer. And then we also have this callback, which we also have to link to the actual timer PWM pulse finish callback, which stops the DMA transfer and sets the DMA complete flag. Jumping over to the .c file, let's look at the init function first. We initialize the PWM timer, which isn't strictly necessary, I believe. We clear the DMA buffer, and this is important because we set all of the PWM duty cycles to 0, which will be important for the reset code. And then we set the DMA transfer ready flag to ready, just to indicate, okay, we can update the colors from now. The set color function takes in the index of the LED, it takes in the R, G, and B values, and these are values between 0 and 255. Remember, we have 8 bits or 1 byte of data per color, so per green, red, and blue. Therefore, values between 0 and 255 are set within that union, depending on the index, and the index is the LED index. Now we have the update function, which is essentially the main part of our code. We want to check if the previous transfer has been completed, or the previous DMA transfer, so we check for that ready flag. We return if we aren't ready. Now comes the main part of the code. So we want to loop through our RGB LED data. Our RGB LED data is set after we call the set color command. We want to take whatever's in the LED data unions, and we want to use that to fill the DMA buffer, which we saw previously. So we loop through all of the LEDs first of all in this outer loop. In my case, that's between 0 and 1, so index 0 and index 1. So for each LED, then we want to loop through all of the bits in that specific LED we're on. We look at a bit of the LED, we determine if the bit is on or off. If the bit is off, we send the low code PWM duty cycle. If the bit is on, we send the high code PWM duty cycle. So the way we can check if a bit is on or off, this is where this union comes into play because we've set the RGB values, but now we can just simply look at the uint32 data, which is a 24-bit data value. We can right shift that by our bit index and all that with a bit mask of simply 1. This tells us if that bit is set or not at a particular bit index. So if that bit is set, we simply assign the current index in the DMA buffer a high value, which we pre-computed, which is our PWM duty cycle for a 1 code. If the bit isn't set, then we assign the DMA buffer current position to the 0 code or the low value. And then we simply increment the place in our DMA buffer index. For this particular scenario, then we're looping through 48 values. And of course, our DMA buffer is longer than that. But remember back to our initialization function, we cleared the DMA buffer beforehand, which means our reset pulse is already given. Our DMA buffer length has already been pre-computed to make sure we have 80 microseconds of 0% duty cycle pulses. Then we can attempt to start the DMA transfer using this HAL tim PWM start DMA. We call the timer handle, the channel, we pass in our DMA buffer and set the DMA buffer length. And if that returns HAL OK, we say, okay, we've started the DMA transfer successfully, let's clear the DMA complete flag. Then we wait for that to transmit in the background, and of course we can do other things because now we're using DMA, and at some point we want to call the callback, which then stops the DMA transfer and sets the DMA complete flag, which was checked, remember, in the SK6805 update function. Then moving over to main.c to actually use this driver, what we need to do is of course include the driver header, then create that callback function. If I could just control click on this, this takes us to the haltim.h file, and this haltim PWM pulse finish callback is actually predefined, but it's a weak function, so you can use that function definition, move it over to main.c or wherever you want to use it, and that then gets called because of the interrupt when the PWM pulse is finished, so after our DMA transfer. So in that function, all we want to do is then call the callback we set, and remember that was to simply stop the PWM DMA stream and set the complete flag. In int main, after all of the initialization, we also want to call our SK6805 init function, which just sets up the DMA buffers and so on, and then we can start doing something useful, so to speak, with our LEDs. So the main calls we want to do are, of course, set color. First of all is the index. So in my case, I just have two LEDs. So it's index 0 or it's index 1. And then we set the red, green, and blue values. So here I'm just doing a very, very simple sequence. I'm just looping through maximum brightness red, maximum brightness green, maximum brightness blue. All I'm doing that just simply with a sequence. So I'm setting the color, and then the update function is actually what updates the LEDs with filling our DMA buffers as we saw, starting the DMA stream with, of course, the reset code to latch the LEDs. And this will do both of those LEDs. So we call the set color and then the update function. And the remaining steps here are simply to switch between red, green, and blue. Then I simply have a delay, half a second delay, 500 milliseconds, and that just loops over and over again, just as a very, very simple demo. But then quite nicely, because you've written this driver, all you have to do is initialize the SK6805, set the colors whenever we want to, and whenever we want to change the colors, we call our update function, and don't forget the callback as before. I'm powering the device simply via USB connected to my computer, and I'm programming the device with an ST-Link V3 connected to my computer via this Tag Connect Edge Connect probe, which connects via castellated pads to the serial wire debug lines of the STM32 U5 microcontroller. And with regards to probing, this test pad you are seeing where my mouse cursor is in the bottom right-ish is where I can probe the RGB LED input, which is the output of the timer channel over here. So now let's upload this to the board. I have USB power connected and my debugger via the Tag Connect cable. Simply click run, it'll build, and then upload the code to the board. So let's check that out on an oscilloscope, as well as see what this looks like in the real world, so to speak. I've now just captured one of the waveforms from the STM32 microcontroller to the first RGB LED for a maximum brightness red signal for both the first and the second RGB LEDs. So green and blue are off, and red is at maximum brightness for both LEDs. And as expected here, we have these various changing PWM duty cycles. We should have 48 bits in total, and we see we have this symmetrical waveform because I'm controlling both RGB LEDs to be the same colors. So we have 24 bits first, then another 24 bits, and then we have our at least 80 microsecond reset code following that. If I zoom in a tiny bit, you can already visually see the first 8 bits are different to the 8 bits that follow afterwards. The first 8 bits correspond to the first LED green, then first LED red, 8 bits, and then the first LED blue bits, and then the same thing repeats for the second LED. Because this is red at maximum brightness, of course we want green to be all 0, blue to be all 0, and red to be all 1 codes. And that's exactly what we have here. If we zoom in a bit, we can see the first 8 PWM duty cycles have a lower duty cycle than the following 8 bits, which should all be a 1 code. So we have green 0, red maximum brightness, blue 0, and then the same thing for the second RGB LED, and then that reset code, where our line is held at a logic low. If we zoom in to the first duty cycles, just looking at the period as well as the on and off times, I've added in some measurements on the right hand side. We can see the period is about 1.25 microseconds, which corresponds to a frequency of 800 kilohertz. That's correct. We have a positive duty cycle of 24%. And remember from our code, our low value is 24% duty cycle. Then if we move over to the right hand side, those red bits, let's zoom in, they should all be 1 codes. And we can see here, still period, of course, constant at 1.25, but the duty cycle is now 48%. And that's exactly what we defined for our 1 code, our high val. So this is looking great. Now let's see this in the real world where the LED is running, just to confirm. Thank you very much for watching this video. I hope it was helpful and useful and showed you how to integrate addressable RGB LEDs in your own designs, both from a hardware and software standpoint. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest embedded systems design videos. Thanks again for watching, and I hope to see you in the next one. Bye bye.